All right, these are the solutions to calculus homework number 31. So for number 1, we have the graph of a function that is given as f of x, and we have the derivative of that function given, f prime of x, and we want to determine the equation for the tangent line at, we're assuming, x equals -1 and at x equals 1. So the first task is we need to determine for sure which of these is the derivative and which is not. So we'll start just by looking at zeros. So we have a location where, let's assume for a second that the red is our derivative. So if we say that red is f prime of x, then we should say that the slope is 0 way off to the left, and then it is positive throughout in the center, and then it is 0 again way off to the right. So if we take a look at this, it is very obvious that the blue does not have a positive slope throughout. Therefore, it must be the case that, we'll use orange here, it must be the case that the blue is f prime of x, and the red is f of x. Let me write that a little more cleanly. So the red is f of x. So I'm going to go ahead and erase this now that we've decided. So we want to determine the equation of the tangent line at x equals -1 and x equals 1. So in order to do that, we need 3 things. So first off, we'll start with the x equals -1. So we need 3 things. First off, we need f of -1. And that is going to be, if we go to our red function, -1, the value for the function is 2. And then we need f prime of -1. Oops. And so now we go to our blue function and say, okay, at -1, what is the value of f prime? So it also appears to be 2. So is that enough in order to write an equation? So we need a point. So our point is -1 and 2, and we need a slope. And now we can write our equation. So at x equals -1, we have y minus our f of -1, which is 2, is equal to our slope, which is the value of our derivative, which is 2, times x minus our -1. So we'll just say x plus 1. So this is a perfectly acceptable equation for the tangent line at this point. Now for x equals +1, we need, again, the value of the function at x equals 1. So we go and look at our red function, and the value of the function there is 2. Then we look for our derivative at 1, and we go to our blue function, which is our derivative, and that is -2. And so now we construct our equation in point-slope form. We have y minus our y value, which is 2, equals our slope, which is -2, times x minus our x value, which is 1, and that is our equation for the tangent line at that coordinate. For question 2 through 4, we're going to be using symmetric difference with our h, our difference, our step, to be 1/1000th, and we're going to use that to estimate the value of the derivative at these values of x, and then write the equation for the tangent line at that x. So my very first step is I'm going to take this function, which I will highlight, this f of x, and I'm going to put this into y1 in your calculator. So y1 in your calculator. So take a moment and do that if you've not done so. And once you put this into your calculator, then I'm going to go to my table. And hopefully your table is in ask mode. If it's not, I suggest you do that. And we're going to get values for our 2x coordinates. And so what do we need? So at x equals 0, we have 2 columns, our y1 and our y2. And so I'm going to write this exactly how I see it on my calculator. I have a column for y1 and a column for y2. And actually this is a column for x, now that I think about it. And so our y1 gives us the value of our function. So y1 is giving us the value of f of x, and our y2 is actually giving us an estimate for the derivative at that coordinate. So for y1 at x equals 0, I have a function value of 0, And for y2, I have a derivative value of 1. Then, for my other x value, I'll plug in x equals 2, and I get a y1 of 5.49. We'll round that a little bit. And a derivative value of 6.06. So let's translate this to two equations. So my tangent line at x equals 0 is going to be y minus my function value, which is 0, equal to my derivative, which is 1, times x minus my x-coordinate, which is 0. So simplifying this a little bit, we simply get y equals x as the equation for our tangent line. Then, at x equals 2, we're going to have y minus our function value, which is 5.49, set equal to our slope, which is our derivative, so 6.06, times x minus our x-coordinate of 2. And so this, we really don't need to simplify much, is the equation for our tangent line at x equals 2. For question 3, we're going to do the exact same thing we did for 2, which is we're going to replace our y1 in our y equals with this function e to the negative x squared. So take a moment and do that. And be very careful about putting this in correctly. Make sure that you have a negative, then an x, then square that x. So from here, again, I'm going into my table that is in ask mode. And given we already used a 0 value for the previous function, we will get, again, kind of a table that looks like this. We have x, y1, and y2. Our x-coordinate that we care about is 0. Our y1 value is given to be 1 at that value of x, and our y2 is 0. So the equation for our tangent line will just be at x equals 0, y minus our function value, which is 1, equals our slope, which is 0, times x minus our x-coordinate of 0. So this whole right side is 0, which means our tangent line is just y equals 1, which is a horizontal line. Now, we can go on and do the exact same thing for question 4. So question 4, we'll change colors. We're going to put a different function in for y1. And we are going to, again, go to our table in ask mode. So we can put in our coordinates that we care about. And our table will look something like this. So we have x, y1, and y2. So our x-coordinates are going to be 0.5, 2, and 4. So once we put these coordinates into our table, we have several different values. So our y1 at x equals 0.5 is going to be, and we're going to round this a little bit, 7.56. And our y2 value is, so it's given as negative 4e to the negative 6. So this is essentially 0, because remember, symmetric difference just gives us an approximation. This is negative 4 billionths, basically. So this is a very tiny number, which we're going to say is approximately 0. Then at 2, our y1 is 1.506. I'm going to go ahead and write all of that. And then our y2 is negative 3.614. At 4, we have 3.5 e negative 4. And our y2 column is negative 0.0021. So while this one is really small and we're approximating that as 0, this negative 4 times 10 to the negative 6th, I am not going to approximate this as 0, although I could. So let's leave it off and not approximate that one while we're doing this. So let's go ahead and write our equations. So at x equals 0.5, our equation will be y minus our y function value, which is 7.56, equals our slope, which we said is 0, times x minus 0.5. So this whole side is 0, which means my tangent is actually just a horizontal line again of about 7.56 y value. Then we're kind of running out of room. So at x equals 2, our function would be y minus our function value, y1, which is 1.506, equals our slope, which is negative 3.614, times x minus 2, which is our x-coordinate. And we can go ahead and just leave this one as it is, unless you wanted to put it in point-slope form, or in slope-intercept form. And then finally, at x equals 4, we have y minus, let's go ahead and just write 0.00035 equals our slope of negative 0.0021 times x minus 4. So it really does work out to be almost 0, but this way it appears that we didn't just assume it was 0. Finally, for question 5, we have one more go through of this exact process. And that means I'm going to take this function and put it into y1 in my calculator and then go and look at my table. And so I will have an x, y1, and y2 in my table. And so I have 3 x values I need here. So I have 0, 1, and 2. And from my table, I get the following values. So my y1 at x equals 0 is 1, and my y2 is negative 1 e negative 6, which if it's to the negative 6th, we're going to go ahead and say that's 0. Then at 1, we have a y1 value of 4 and a y2 value of 5.2274. And then at x equals 2, we have a y1 of 5 and a y2 of negative 4.047. So for our equations, at x equals 0, our tangent line will be y minus y1, which is our 1, equals our slope, which is 0, times x minus 0. So again, we have a horizontal tangent line of y equals 1. At x equals 1, we have y minus 4 equals our slope of 5.2274 times x minus 1. And we really don't need to simplify it. We can just leave it as slope or point slope. And then finally, at x equals 2, we have y minus 5 equals negative 4.047 times x minus 2. And there are all of our problems where we are using our symmetric difference approximation. So question number 6 is a very interesting conceptual question that basically tests your understanding of how this equation differs from what we have above. So in case you've forgotten what we have in notes, we have the equation for a line can be written as y minus f of a equals f prime of a times x minus a. And so this is the equation for a tangent line at x equals a. So the difference, I can highlight, the difference is right here, which is the difference between f prime of a and f prime of x. So what is the difference between these two? Well, f prime of a means the derivative's value at the a coordinate. If I write f prime of x, well actually let's go ahead and write. So f prime of a is the slope of f of x at x equals a. F prime of x is this slope anywhere. So that's at any value of x. So the only case where f prime of x and f prime of a would be the same is if the slope is constant everywhere. So this only works if f prime of x is a constant. Or you can think, so you can say, I'm going to say, or this is the same as if f of x is linear. Now we get to our textbook problems. And so our first problem has to do with some cost as a function of the weight of a chemical. So question A asks us to interpret, I'm going to zoom for a moment, asks us to interpret the statement f of 12 equals 5. So we know that cost is defined as a function in terms of w, which is weight. So our weight is the argument of our function. So this is the 12. So this is weight, which means that our units are going to be pounds. So the units of the 12 are pounds. I'm going to just highlight this, I think, as the answer. So that is our first answer. Ooh, let's use yellow. Then our 5 is cost. So this is our cost. Oops. So this is our cost, and our cost is measured in units of dollars. So that would be the units of the 5. Switch to highlighter, huh? Now, the next portion says, do you expect the derivative of, or actually, so explain what this, so the next part is explain what this says about the cost of buying the chemical. Well, basically this is saying that if I buy 12 pounds of the chemical, that will cost me $5. So 12 pounds of the chemical costs $5. It's just an interpretation of this function statement. Now, B says, do you expect the derivative f prime to be positive or negative, and why? Well, given that the more stuff you buy, you tend to have more cost, I would expect f prime to be positive. Basically, I'm saying that the slope should be positive because more stuff, more chemical, should cost more. Now the last question, part C, says, in the statement f prime of 12 equals 0.4, what are the units of the 12? So the 12 is again the argument of my function. So this is again weight, and so that should be in pounds. Then what are the units for the 0.4? So this is my derivative, right? And so I'm trying to think here, this is how my cost changes with respect to the amount of stuff I'm buying. So this is no longer just dollars. This should be dollars per pound. Right? It's how does the cost change as a function of how much weight I am saying. So it's how cost changes, and I'm going to say with respect to, WRT, weight. So that would be dollars per pound. And we'll go ahead and highlight these, my answers, to make sure. So we have dollars per pound and pounds. Question 6 says the time for a chemical reaction T, measured in minutes, is a function of the amount of catalyst present, A, in milliliters. So we have T equals some function of A. Now, question A, or part A, says f of 5 equals 18. So what are the units of 5 going to be? Well, A, which is the argument of my function, is given as the amount of catalyst in milliliters. So this number 5 here is the amount of catalyst that we have. And that is measured in milliliters. I'm just going to write ml, which are the units milliliters. Let's actually use the highlighter again. So the 18, however, is my t. So this is the time for my reaction. So this is time, and that should be measured in minutes. Now, what does this tell us about the reaction? That means 5 milliliters of catalyst in my reaction means it will take, so the reaction will take 18 minutes. So that is the interpretation of this function's statement. Now B says, if f prime of 5 is negative 3, what are the units of the 5? So the 5 is still amount of catalyst. And that's in milliliters still. And then the negative 3 is now, how does the time change as a function of the amount of catalyst? So it's the change in time with respect to amount of catalyst. So if I plug in a certain amount of catalyst, how much longer or shorter will the reaction take? So the units for this should be minutes per milliliter. And so these are the units for my slope, and these are the units for my argument. So what does this tell us? If negative 3 is the slope, that means adding a milliliter of catalyst decreases the reaction time by 3 minutes. So question 7 is similar to our last two questions, just another way to interpret our statements in terms of functions. So we're back to our economy, where we have a price, which is in dollars for P here, and a quantity, Q. So we have Q is a function of price. Quantity is a function of price. So for A, if we have the statement F of 150 equals 2,000, that means that if the price, actually we shouldn't say if, we should say a price of $150 means you will sell 2,000 of an item. So that is our interpretation of this first statement. Now the second part of the statement says, or our part B says, f prime of 150 is negative 25. So what does this mean? So this is our change in quantity as a function of price. So let's go ahead and write that. Change in Q as function of P. So what does this mean? This means that so increasing price from $150 to, let's say, 151 will, actually we don't need a comma here, will, too many L's, will decrease the quantity sold by 25. Now you can actually write this several different ways. You can say that a change in cost or price by $1 will decrease the quantity sold by 25. But the point is that we only know this derivative value at 150. So this doesn't necessarily mean that always a change in price of $1 will decrease the quantity sold by 25. We just know that really at this one location or this one price.